So lesson 2, we spent 2 days on Newton's laws to wrap our brain around them because they're not intuitive, especially Newton's first. Newton's second law, F equals ma. A spacecraft has a mass of 3.25 times 10 to the 4th kilograms. Its engine can exert a thrust force of 7.25 times 10 to the 4th newtons. Logan, what does A want me to find? No. Last word. Yeah. Remember how tough word problems were at the beginning? Now you're spotting the physics words because you said mass and you caught yourself right away. No, it's not. Yeah, acceleration. Now, acceleration is one of those things where I can find it a whole bunch of different ways. This looks like a mass. This looks like a force. Logan, I think I'm using this one to find acceleration, not VF equals VI plus AT and not all the other ones. So how would I get the A by itself, Logan, my friend? How will I move the M over? So you're telling me. Now, you'll notice since Christmas is over, Savannah, I'm not forcing you to do the defic thing as much. You can still, if you want to, go A equals question mark, F equals and M. But if you're comfortable enough now that you can skip that step of listing everything, and if you feel, Savannah, that you can go straight to the equation, Sam, go ahead. We've done enough now that now we're at the point where if you want to start taking the odd shortcut, as long as you're always getting it right, I'm okay with that. Logan, what was the force in newtons? What was the force in newtons? Read it to me. No, what was the force in newtons? The number. Go look at the question. Just that right there. What was the force in newtons? 7.25. Keep going. Times. Okay. That's the force in newtons. I just looked for the N. Yes? Yeah. Is there a kilogram somewhere for mass? Read me the mass, kiddo. Okay. What will this spacecraft accelerate at? Again, please make sure you're practicing typing in on your calculator. Today, and especially 2 classes from now, we're going to be doing some pretty complicated equations. If you haven't practiced typing these in, you're setting yourself up for ugliness. Do you have a calculator here? Oh, is it out? Okay, sorry, I was screened. 7.25 scientific notation button 4 divided by 3.25 scientific notation button 4. And I get 2.23. That looks like a good place to round off. And Logan, units for acceleration, meters per? Yeah. I know, we're brushing off the cobwebs still from Christmas. Okay. Is that big? Is that bigger than 1G or less than 1G? That's less than 1G. You could feel it, but it wouldn't be like you'd be sitting there feeling a whole bunch of mass pressing on you or anything. Okay? If the spacecraft maintains this constant acceleration for 12 minutes before shutting off the engine, and its initial velocity was 5.6 times 10 to the 3 meters per second. Hey, Rowan, what's this question asking me to find? I think you're right. VF, right? Okay. What did we find in part A? Yep, let's remember that. What's this right here? 5.6 times 10 to the 3. VI. What's this 12? It is, and it is. Why is it time, and why is it also not time? Why do I kind of look at that and say, okay, you know what I would do right now? Cross the 12 out, and right above it, how many seconds is that? How do I go from minutes to seconds? That's often I'll do that if I see bad units right away, just so I don't later on fall into the trap of mechanically plugging and chugging, right? Is it 720? Okay. So we're going to fire our engines for 720 seconds. How fast are we going? Which equation can I use? I did say you didn't need to get out your formula sheet. I realize that. I'm gambling that you have this maybe in your mind, but if not, that's fine. Now here, if you're not sure and you wanted to go VF equals question mark, VI equals 5.6 times 10 to the third, T equals 720, A equals 2.23. It's our old friend. Yeah. Plus? Yeah. So VI is 5,600. That's what 5.6 times 10 to the 3 is, but that's easier to type. Plus A. I'm going to write 2.23, but I'm going to use my answer button on my calculator. Times 720. 5,600 times answer button. No, not times, Mr. Dueck. Plus answer button times 720. Typos galore, Mr. Dueck. 720. You get 7,206. Let's go to 3 sig figs. So that 0, is it going to stay a 0 or become a 1? So I'll go 7,210 meters per second, which is pretty fast. You're doing about 7.6 kilometers a second. You're hauling. Not escape velocity, by the way. Escape velocity is about 11.1 kilometers a second. So this wouldn't get you away from the Earth. Evan, what's C want me to find? You know what? I listed the stuff here. I got a VF, a VF. You know what? I think I can use these and not even use VF. Which equation, kiddo? Yeah. I'm purely brushing some cobwebs off right now, reminding you all of those are still fair game. Why? Because F equals MA, which showed up in a lot of those too. Okay? It's going to be 5,600 times 720, not 12 minutes, seconds, plus 0.5, 2.23, 720 squared, 5,600 times 720 plus 0.5 times 2.23 times 720 squared. Can you double check me? I got 461, 2 zeros, and a 16. I think this number I am going to write in scientific notation because it's big. 4.61 times 10 to the what? Yes. $4.6 million meters. Okay. Well, yeah, it's going 7 kilometers a second. It's hauling. What will the velocity of the spacecraft be after 48 minutes? It's a trick question. Can you go back and see which words did I underline? Kenzie, which words did I underline? So, we're shutting off the engine. How fast will we be going after 48 minutes? No. Because what does Newton's first law say? In outer space where there's no forces acting on you, you're going to keep going in a straight line at a steady what? At a steady what? Speed is, I think, the phrase I've used. Steady what? Speed. What was our speed when we shut off the engines? 7,210 meters per second. How fast are we going after 48 minutes? 7,210 meters per second. How about after 60 days? 7,210 meters per second. And this is how we're able to get space probes out to Pluto. The New Horizons one you saw a couple of weeks ago was showing us some neat images. It's way out there. This is how the Voyager probes have managed to leave the solar system. We gave them a push in outer space and we let them go. The Voyager probes have been going for over 30 years. Took them a while to leave our solar system. The New Horizons is going way faster. Probably in a decade or so, it will have traveled further than the Voyager probes. It won't pass them because they're not going in the same direction. Why would we re-explore an area of the solar system we already know? We sent the New Horizons in a different area, different way, okay? But, so the answer here is 7,210 meters per second. Why? What law did we use? Newton's first. It is one of the nice things, Rowan, about space travel. If we do ever accomplish regular space travel, what we'll do is we'll fire the engines and then shut them off and coast. Okay. We might not. It all depends. While the engines are firing, what were we accelerating at? You'll have to look. I've scrolled down. And what that means is, if the spaceship is traveling forwards relative to us, the wall would act a little bit like a floor, except gravity wouldn't be 9.8, it would be 2.23. But there would be some simulated gravity. And that makes things way easier. For example, you can eat food properly because it will stay in the plate, not float around. You can drink beverages because they'll stay in their glass, not float around. Once you shut the engines off and start coasting, now you're back into complete weightlessness, and all of the things that you've seen in the movies would occur. So I don't know. That's just kind of a setup, Kenley. Are you ready? Good stretch? Here's the lesson. Free body diagrams, FBDs. A free body diagram is a picture that represents the object that we are analyzing with a dot. Any of the forces acting on it are represented with arrows, roughly to scale. And what I mean by roughly to scale, if I know one force is bigger than another force, I'll make sure that arrow is longer than the other one. If I know that two forces are the same size, I'll try and eyeball their arrows so that they are the same size. Newton's laws are used to figure out what forces are acting on an object. Here are 4 free body diagrams shown below. The only thing is they didn't represent the mass with a dot. They represented it with a square. I'm lazy. I would have just put a big dot in the center instead of a square. But they've given us the net force, and we need to figure out missing forces. Show you what I mean. Good yawn, Jabber? Good, because you're on. What's the net overall force here? So that means all of the forces are, I'm looking for where the begins letter B. Okay. It says that this is 50 newtons. How big must A be exactly? Has to be. How big must B be exactly? Don't say 50. Has to be 200 newtons exactly. Second situation. It says the net force is 200 newtons up. How big must C be then? And don't say 900. Sorry, did I say the net force is 200 newtons? The net force is 900 newtons up. How big is C? And don't say 900. It can't be. Can't be 700. 700 would give me 500 newtons net force. 1100. 1100 up plus 200 down gives you a net force of 900 newtons, unbalanced. By the way, I'll come back to that question. Okay, the net force here is 60 newtons to the left. How big must D be then? This one's tricky. It's got to be 20. How big must E be? Because it doesn't say it's accelerating up or down at all. Now, here's what that means. In the up-down direction, it could be at rest, or it could be moving up or down in a straight line at a steady speed. I don't know. All I know is it's not accelerating. I can't say that it's stopped. I can't say it's not accelerating. I know it's accelerating to the left. It has to be from this diagram. Ooh, how big must G be?
Wait, in the last one?
Yeah.
If it was accelerating left, wouldn't the right side be good?
Pardon me?
Wouldn't the right side be good?
No, it's accelerating that way. Who's winning that way? Okay? And in fact, that's what we're often going to ask, is we're going to say, who's winning? Which is the winning force? That's our bigger force. How big must G be?
50.
That gives me a net force of 30 newtons to the right. How big must F be compared to H? Yeah, even though I don't know what they are as numbers, I can tell you beyond a shadow of a doubt that that must be true. If I was drawing arrow lengths and if I was marking your question, I would look for arrows that look pretty much the same size. In other words, if you drew this, I'd take a half mark off and I'd say, are you kidding me?
You got 20 people from that fine?
20 for both of them?
Yeah.
It's not 20. Could be 100, could be 100. Could be 80, could be 80. This has nothing to do with that. All I know is those two have to be the same. Okay? I think there's a part 2 to this, is there not? Yeah. No. Oh, no. It says analyze each. Yeah.
For the last one,
Yeah.
for you to get the marks for the top and the bottom, do you just write the opposite?
I can't answer that because I'm not going to give you a question like this. I'm just right now planting the idea of a free body diagram in your mind. Now let's actually bring in some actual numbers. Okay? So I would say I don't think I like example 2. I kind of like example 3. So example 3 says this: a book is at rest on a tabletop. A free body diagram for this situation looks like, let's represent the book with a dot. All of you can look at the binder that's in front of you. Okay? I like to do free body diagrams, Savannah, very systematically. So you're going to hear me go very meticulously. So I'm going to say, look at the binder sitting on the desk in front of you. What are the forces acting on it? Get the obvious one. And by the obvious one, I mean gravity. So draw an arrow pointing down. And I'm about to answer your question, Kenzie. Is the binder sinking into the ground like quicksand? Is it flying into the air like Superman? So the forces must be, I'm looking for, it begins letter B. So here's what I would look for in your free body diagram. However long you drew the down arrow, the up arrow should be pretty much the same. I would take a mark off if you did that. Okay? But I'll give you, because I suck at drawing, I'll give you a fair bit of leeway. If you did that, even though I suspect if I pulled out my ruler, that top one is technically a tiny bit longer, I'm not going to freak out. It's if you've obviously not got the concept. We're going to call this F, how about table? That force there, pushing up, that's a Newton's third law force. The book pushes on the table, forces come in pairs, the table pushes back on the book. But I know it has to be there because if it wasn't there, your book would be sinking into the ground like quicksand because I'd have an unbalanced force pointing down. Do you see what we're getting at, Kenzie, with all the pictures? That's what I'm trying to get at, okay? A classic example we'll look at is a mass hanging from a rope. So it says, draw a free body diagram for the following masses hanging from a rope. So I'm going to represent the mass with a dot. Now, the first situation, we are at rest. What are the forces acting on this mass? Get the obvious one. Okay. Force of gravity. By the way, I jumped the gun just a tiny bit if you look up. Normally, I write force of gravity. Here, I already wrote the equation for the force of gravity, which I kind of showed you, but I'll show you in more detail later. So I hope I didn't confuse you. I used MA, so you can write FG or MG. Is this accelerating down? No. Is it accelerating up? So there has to be a force pointing up the same size as gravity. So however long, Logan, that you drew your arrow for gravity, eyeball it, draw another arrow the same length pointing up. Mine's too long. Ish. What force is that? It's the rope. We have a special name for the force in a rope or a cable or a string. We call it tension, capital T for tension. Same situation, 12 kilograms, but now we're accelerating up at 2 meters per second squared. This is a job for a free body diagram. What are the forces acting on it? Get the obvious one. FG or MG. What else? Is there a rope? Tension. Am I going to draw tension bigger, smaller, or the same size as mg? And how do I know? Why? Because it's accelerating up. If it was moving up at a steady speed, is it accelerating? So I would still be the same. So I got to be fussy. You said because it's going up. It's because it's accelerating up. And I tend to exaggerate it so it's obvious to me so that I don't miss it later on when I come back and look at the question. I glance at that. To me, it's pretty obvious tension's winning, the bigger force. By the way, which of these ropes is more likely to break? Yeah, because tension's bigger. Same mass, but we've just increased tension. Now, that's kind of Captain Obvious, but when are you most likely to break a rope? If you yank on it up. There's the physics of why. Okay. Turn the page. Some types of forces, Savannah. One of the forces that you're most experienced with is the force of gravity. You've known it all your life, unless you, like me, have jumped out of an airplane. I mentioned I jumped out of an airplane. This is the force that the Earth's mass exerts upon you. And the force of gravity is calculated as follows. Well, first of all, F equals what? Ma. And we use the letter G for the acceleration due to gravity. So it's mg. Rowan, you have your formula sheet. I think I gave you Fg equals mg as the second equation in this unit on forces. I think the first one is F equals ma. Yes?
No.
I'm waiting for you. Find where it says forces. No, it's front page. About halfway down. Okay, and F equals ma, right next to it, Fg equals mg. And did I also tell you on your formula sheet another word for gravity? For the force of gravity? Where it says F... Oh, no, now. You got the... Wait, no, now. Wait, no, now. Okay. He figured it out. Okay. I'm going to be fussy on this on your test or on a quiz. If I ask you for an object's weight, don't tell me kilograms. Weight is a unit of force. It's measured in newtons, not kilograms. So how do I change kilograms to newtons? I multiply by G. Or as a number exactly, I multiply by, you all know this number, 9.8. Not negative because we're talking about a magnitude, okay? So it says this, find the weight of a 35 kilogram object on the Earth and on the moon. You know what? Let's go like this. Here's the Earth. Here's the moon. Ben, what does this question want me to find? Hoping you'd just say the word weight, and I was going to say no now. But the weight, fine, you wrecked my punchline. Yes, you are correct. It wants me to find the force of gravity. The word weight is a synonym for force of gravity. It's not mass, Logan. Mass is in kilograms. Weight is a force in newtons. So all of us, let's write down Fg equals mg, and then I'm going to put a little Earth. And on the moon, Fg equals mg, and I'll put a little subscripted moon. Does your mass change on the moon? No. What changes? The acceleration due to gravity and your weight. Your mass doesn't change. Your weight changes. The force of gravity pulling on you changes. In fact, Rowan, your mass doesn't change anywhere near the universe. Even near a black hole, your mass is your mass is your mass is your mass, whatever it is in kilograms. What does change, depending on what planet you're nearby, is your weight. That all depends on the gravitational field strength of the planet that you're by. Okay? So for the Earth here, it's going to be 35 times 9.8. I can do that in my head. It's going to be 350 minus 7. 343, double check me. I think it's 343. Yeah? I can do math in my head. Units, weight, it's a force. By the way, if this was a multiple choice question, would I also have one answer that said 343 kilograms? Maybe. Okay, because I want you to realize it's a common misuse in the English language. Weight and mass are not the same thing. On the moon, it would be 35 times 1.6. I think I can do that in my head. It's going to be 35 plus 21. 54? 56! Ah! I forgot to carry it. Okay, 56 newtons. And so you feel lighter. This is important because I'm a physics nerd, Savannah, not because your mass has changed, but because what has changed? I'm looking for where it means letter W. Now. Yeah, your weight has changed, okay? That's why, by the way, the astronauts on the moon were able to wear such bulky spacesuits on the moon. On the Earth, the weight would have been about 300 and some pounds, and they would have had a terrible time moving. On the moon, no problem. Lots of mass, little weight. You've seen videos of them walking on the moon. There's a great video, I think on one of the later moon landings, where an astronaut is singing to himself, "I was strolling on the moon one day," and he starts to almost giggle, hippity hop, because he's able to leap so easily. He's kind of hopscotching, and even though he's trying hard to be professional, there's enough of the inner child within him that he just gets a giggle attack and just starts thinking this is the coolest thing. So weight is one of our forces. Force of gravity, mg. To solve force situations, and this is the only tool I'm going to give you in Physics 11 and in Physics 12, we're going to use a tug-of-war analogy. We're going to draw a free body diagram. We're going to label all the forces. We're going to figure out, Jackson, if any are missing by using Newton's laws the same way, or which ones are bigger the same way on that second tension question. We said, well, that arrow's got to be bigger because it's accelerating up. Then we're going to use or figure out which way we're accelerating, which way is the winningest or the strongest force. And here is our generic equation. I don't know if I put this on your formula sheet. This is, I said to you at the beginning of this unit, the problem is I can't give you, here's the equation for everything. I guess this sort of is, but you're going to then have to, Kenley, adapt it for each situation. It goes like this. Winner minus loser equals F net, the net force. Winner minus loser equals the net force. Although the net force is equal to F equals what? F equals what? So you'll often see me think to myself, winner minus loser equals MA. This is what's going to allow us, Rowan, to handle or solve any force situation out there. A surprisingly large number of situations. With a little bit of cleverness, Logan, this can handle it. So in this situation, unlike before Christmas where I gave you equations to fit every situation, here I'm saying this is it. We're going to adapt it. Next page. Suppose a box is resting on ice and the following forces are acting on it. There's a force to the left of 6 newtons and a force to the right of 14 newtons. A says, add any forces that you think are missing. Okay, what are the forces acting on this box? Get the obvious one. Is this box sinking into the ice like quicksand? Is it flying into the air like Superman? Then in the vertical direction, the forces must be, I'm looking for where the begins letter B. So I know there has to be an equal size arrow. However long you drew your arrow, draw an equal size upwards pointing arrow. And that's going to be the force of the ice, F, with a little subscript ice pushing up. I know that has to be there. So A says, draw any forces that you think are missing. Actually, these are forces that I know are missing because I know gravity's there and I know it's not accelerating in the direction of gravity. Okay. So is it going to accelerate up, down at all? Which way will it accelerate? How do you know? Newton's first. Which way is there an unbalanced force pointing? Okay, I'm going to ask you the same question. I want the same answer. I'm just going to phrase it differently. Who's winning? Who's losing? So here's how I can come up with my equation. In our notes, we're going to write more steps. Eventually, you'll get good enough at this, Sam, that in your homework, you'll take shortcuts. But here's what we just thought to ourselves. We said, okay, winner minus loser equals MA. Who's winning? 14 minus who's losing equals pause. What does B want me to find? How would I get the A by itself? And do you mind? I'm going to put the A equals over here on the left because that's where we're used to seeing the thing that's by itself. I'm not putting that equation on your formula sheet because as soon as I add another force, it's a completely different equation. What I am saying is who's winning, who's losing, that equals MA. That'll get me through all this. By the way, on the top, I have 14, take away 6. I can do that in my head, 8, and the mass is 3. This must accelerate. What is 8 divided by 3? I think it's 2.6 repeating?
Yeah.
2.67, let's say. Logan, units, it's acceleration. Meters per,
Seconds per.
thank you. And if they had asked for a direction, right or east or something, they just kind of said how fast. I think that's implying all they want is the magnitude. Okay. Winner minus loser equals MA. That's sort of the generic template that I'll give you, but Ben will have to adapt the rest. Suppose the box below is sitting on a table and it's accelerating to the left at 3.2 meters per second squared. Add any forces that you... So I got Abe pulling to the left. I got Billy pulling to the right. I think I'm going to use a capital A for Abe as my abbreviation. I think I'll use a capital B for Billy, and yes, that's why I picked those names, so I can have force A and force B. What else must be here if it's sitting on a table? What forces are missing? Okay, I would definitely have gravity down. Is that all? It would has to be the table pushing up. And draw your arrow, Kenley, the same length as however you drew gravity. Eyeball it. You don't have to pull out a ruler and measure it to the nearest millimeter, but please be close. Okay, so add any forces that we think are missing. We know those are missing. Check. B wants me to find how hard Abe is pulling to the left. Which way is this accelerating? Who's winning? Who's losing? What's it going to equal? MA. Don't overcomplicate it. Winner minus loser equals. So, I don't want to write Abe and Billy. I'm lazy. How about force Abe winner minus force B loser equals MA. Sam, what's this question want me to find? Keep going. Keep going. What's it want me to find? I'm looking for a word that starts with letter A and has a B and an E next to it. Help me out, folks. What's it ask me to find? Abe. Sam, how hard Abe's pulling? Okay? Yes? This in my equation. How would I get FA by itself? How will I move this FB over? Well, Sam, what's right in front of the FB? You're way overcomplicating this. What's immediately sitting right here in front of the FB, right there that my little cursor is moving over? A minus. So how will I move the FB over? Yep. Yep. Do you say plus? Add it, plus it? Yes. Okay. So I get this. You want to know how hard Abe is pulling? It's going to be MA plus FB. I'm not putting that on your formula sheet because that's unique to this situation. Did they give me the mass, Sam? I've scrolled down. What was the mass in kilograms? What was the acceleration? Now, Mr. Dueck, the acceleration is to the left. Shouldn't it be negative? So this unit We're no longer always going to let down be negative or left be negative. We're going to let winner be positive. We're going to let the mathematically most convenient way be positive. And this time we've decided to let that way to the left be positive. So you're not going to somehow insert negatives in for accelerations. It's just going to be 3.2 plus, I've scrolled down, Sam, how big was FB? That's the force of Bill. Okay, are you with me now? Because you way overcomplicated that. You okay? You did. Okay, good. What do you get? Oh, I can do this in my head. 5 times 3.2, that's going to be 15 plus 1, 16. 40 even? Double check me. Is it? Abe has to be pulling with 40 newtons. I put a dot just so I could say I'd gone to 2 sig figs, but you don't have to. Has to be. Okay? Are you starting to see how a good free body diagram can really bail you out? It makes everything clear. And then, Savannah, we're using Newton's laws to figure out any missing forces and who's winning. And I think you turn the page. Is it? Yeah? I like example 6. I like example 6. I like example 6. Example 6 is a nice question. Antonio, what's example 6 want me to find? Like you're feeling right now? A little tension? Shut up. Okay. You know what this is a job for? A free body diagram. I'm going to represent the mass with a dot. Right there. What are the forces acting on this mass, Antonio? Get the obvious one. Get the obvious one. 2 is not a force, by the way. It's an acceleration. Get the obvious. Not a force. What do I mean by whenever I say get the obvious one? Kenzie. Gravity. Start with that because that's going to give you your arrow length reference for all the other ones, whether they're bigger or smaller. So I always start with gravity. Which way is this accelerating? Which way must there be a bigger unbalanced force pointing? So I'm going to draw a longer arrow up. Exaggerate it so it's obvious. Which force is that? Acceleration is not a force. Stop doing that. They're not even the same units. Which force is that? What you're feeling right now. Those are the 2 forces acting on this object. And this is what I meant by roughly to scale. I know which one's bigger. In fact, you ready? You ready? You ready? Look at your picture. Who's winning? I don't know what that means. Say it out loud in English. A word that begins with the letter T has an N on the end of it. That's what you're feeling right now. Okay, so you ready? You know what? Just this once in our template, let's write at the top here, winner minus loser equals M. This is what we're going to be flogging to death here. Okay? Who's winning, Antonio? Now that means any force pointing up is the winner. Who's losing? Mg. What does it always equal? Ma. What did this question want me to find? Sam, my friend, how am I going to get the T by itself? What's right in front of this Mg? Oh, you're saying I would just plus the Mg over? This is why Mr. Dueck was doing all that formula manipulation stuff, because I couldn't possibly come up with every single equation for forces. So you're telling me that tension is going to be Mg plus Ma, or you could have written Ma plus Mg, because 5 plus 6 and 6 plus 5 are the same. When you're adding, the order doesn't matter. Okay, Antonio, what's M? Good, because you know that's kilograms. What's G? You know this number. And not negative. We took care of whether it's negative or positive by going winner minus loser. That's where we inserted our directions. So just 9.8 plus, what's M again, Antonio? What's A? Okay. You're looking puzzled. Did you go, pardon me? Yeah, you wrote MA plus MG. Yeah, I said it doesn't matter which way you write it because 5 plus 6 and 6 plus 5 are the same. I wrote it this way for a reason. You're going to see I'm trying to make it symmetrical with the next question, but that's me being sneaky. What is 12 times 9.8 plus... You know what? I can do this in my head. It's going to be 12 times 11.8. 12 times 11 is going to be 121 plus 12.8. 129.6? No, I'm wrong. What do you get? 141.6. Units. Tension is a force. Newtons. Okay. You okay with that, Antonio? Okay, Jackson, you're up. Are you ready? Jackson, what does example 7 want me to find? You know what this is a good job for? Free body diagram. Let's represent the mass with a dot. What are the forces acting on this mass? Get the obvious one. Yep. Patience. Am I going to draw tension bigger, smaller, or the same size as mg? One of those is correct. That's the good news. Bigger or smaller? Why? And Newton's first says that must be which way the unbalanced bigger force. That, do you see why I spent so much time on Newton's laws as well? So I'm going to really exaggerate it, making sure that it catches my eye that tension is the loser. Winner minus loser equals MA. Who's winning? Jackson, my friend. MG. Who's the loser? Oh, Kenley, did you see that? I said, who's the loser? And he looked at you. Oh! Kenley, Bonson Park, you take care of it for me, okay? Wow. Teammates, wow. Who's losing? Jackson, my friend. By the way, yes, I do that joke every time because right around now we need a good giggle because this is tough. Okay, sorry? So it's going to be minus tension. What's winner minus loser? Always equal. What are we trying to get by itself? What does it want you to find? Sorry, what you're feeling right now? Yeah, what's right in front of the T that I don't like? Right immediately in front of the letter T that I don't like. Blech. So here's what I'm going to do. I'm going to do 2 steps at once. Look up, look up, look up. Everybody watch. One of my students last year nicknamed this the Swappi Dance. Here's what I'm going to do. At the same time, Logan, I'm going to plus this to that side so it's positive. And at the same time, look up, I'm going to minus this to that side. So I'm going to get this. The mg drops down like a domino. There's a minus ma. That equals tension. I always draw the loops, so I'm going to say now, pick up your pencils, draw the little arrows pointing like that so you know what the heck we did. That's the Swappi Dance. And I will do that anytime what I'm trying to find has a negative in front of it. I'll just plus it to the other side because I know from personal experience I'm much more likely to make a dumb mistake, Kenley, when there's a minus. So I can fix that. Easy peasy. I didn't get rid of all the negatives, but I can get rid of the negative in front of what I'm trying to find. By the way, and here, Antonio, is why I wrote it in the order earlier. Do you notice when we were accelerating it up, tension was mg plus ma? When we're accelerating down, tension is mg minus ma? Which tension is going to be bigger? Yeah, because you're adding 2 things together. In other words, when is a rope more likely to break? When you're trying to lift something, accelerate something up. When you're trying to accelerate something down, you got some breathing room. M, 12, 9.8. Mr. Dueck, shouldn't the 9.8 be negative? Jackson and I took care of the negative when we decided who was winning and who was losing. In fact, if you actually look at it this time, we decided to let down be positive because it made the math easier. Minus 12 times 4.2. What do you get? So I know the answer should be smaller than 141 point whatever. What'd you get? Can't be negative. It's impossible.
67.2.
So if you got a negative, please make sure you wrote mg minus ma and not ma minus mg. Because then you did the Swappi Dance wrong. The mg dropped down. The ma got minused over to the other side, right? So what was it?
67.2.
2 more. We'll pause. Example 8. By the way, I like example 6. I like example 6. I like example 7. I like example 7. I like example 8. I like example. There's going to be a tension E question with a mass accelerating up or down on your test because it's a good. You'll notice now we're bringing in Newton's laws, a free body diagram, a little formula manipulation, F equals what, MA, but now I've broadened it into winner minus loser equals MA. Okay, so lots of good stuff here. I like the rope hanging from the mass hanging from a rope. Okay. Kenley, this is your chance to get back at Jackson. What does example 8 want me to find? You know what this is a good job for? Free body diagram. Eventually someone's going to notice that I've said that 4 times in a row and they'll finish the punchline for me, I hope. But that's okay. What are the forces acting on this? Get the obvious one. Yep. Now, by the way, the reason I do that, kids, especially as the questions get tougher, they always want to go into the really toughy mystery force first. Save that for later. If you do the free body diagram systematically, often the mystery force will just kind of drop into your lap. Oh, I know how big it has to be and which way it's pointing. So gravity. Good. What else? Tension, which way? Up. Bigger, smaller, or the same size as gravity? Now, you've made a mistake. Now, this is a tough question. I like this question, Everybody right now, underline that there. What? Say equal to? So the forces are, I'm looking for the begins letter B. But let's do it wrong. Just to show you, as long as we're careful and don't do silly guesses, we've got some safety nets here because it's moving up. And so Kenzie said, Mr. Dueck, I think it's that. So then you would say, who's winning? And you would answer, who's losing? What does winner minus loser always equal? Okay. And then you would say, get the T by itself plus the mg over. And Antonio, I usually go mg plus ma just so that I can notice that when we're going, it was mg minus ma. I just want it in kind of the same order, but you don't have to. And you would say this, tension equals, what's m? 12, g plus, what's m? 12. What's A? And don't you dare say 3.8 because your teacher showed you a video of a poor Verizon customer screaming at an operator trying to explain that units matter. And I hope I've drummed that into you and that you wouldn't blindly say 3.8. I hope you would say, well, it's not the 3.8, and you would start to freak out a little bit. But then you would go read carefully, and you would, aha! Have that moment of constant speed. What's A? And so, actually, I could have just said the forces are balanced, tension equals mg. I could have jumped to this right away, but as long as you're careful and don't put in silly units, hopefully you'd catch that. And this is what Isaac Newton said. He said, if you're moving at a constant speed or you're at rest in terms of forces, same diff. This is why Einstein said, I don't know how to work acceleration in. I can only work in, for special relativity, constant speed. That's what we had to do first. Acceleration was special. It's going to be 12 times 9.8. 12 times 10 is 120. It's going to be 120 take away 2.4. It's going to be 117.6. Or am I wrong? Yeah? What if we were at rest? Also 117.6 newtons, because at rest and constant speed, A is 0 in both of those, and that's all our forces questions help us with, is acceleration, not speed. My rant okay? So I kind of, now I have to do something here. This free body diagram offends me, so I am now going to draw it so the forces do look balanced, because that was fingernails on the blackboard to me. But the beauty of it is, Savannah, as long as you don't put silly units in, hopefully you would catch yourself and say, something's wonky here. Is that all right? We're going to be practicing this a lot more. When? Which is Wednesday? Yes? For now, I'm going to be assigning almost all the homework, but if you want to get a head start, you can try number 1. I'm giving you a whole bunch of rock hanging from a rope. I'm telling you which way it's accelerating and what the acceleration is, and you're going to try and quickly find the tension. I would encourage you, don't try and memorize an equation. Do a quick 1-second free body diagram sketch. That's the best tool I can give you because it means you don't need to memorize the equations. That 1-second sketch helps you figure out the equation. Put your pencils down, look up.